And I wanted to thank you all for coming. People who came from very much abroad, people who came from the places just kilometers far away from here, and everyone. The talks have been amazing. We have been having such a great time. People through YouTube are having such a great time at their places, and we are very happy about having you all here. And we also wanted to invite you to contribute to the Humana Mentes volume that we have the open call until December, the 15th of December, something like that. And we will be very glad to have your contributions, and we will be very glad to read you as well and to watch the videos over and over again. So,
well, I am pleased to introduce the last of the talks for today. This is a Meheus talk, Inconsistency and the Microstructure of Scientific Revolutions, the Importance of Simulations, Simultaneous Living in Multiple Worlds. So I'm eager to see what's going on. Please.
Thank you. First of all, I would like to thank Maria and Luis for organizing this wonderful workshop and for inviting me. I very much enjoyed the long discussions, that we had time for discussions and questions. As some people know, I'm horrible with timekeeping, but I always have too much material, and I'm not able to talk as quickly as Dunya, but I'll do my best to make sure that we also, for this talk, have some time for questions and discussion. So for this last talk, I would like to invite you to make your hands dirty and to look together with me at some examples of the messy stuff in science. We will look at some examples from one of the best-known examples of revolution in science, the chemical revolution. And more specifically, I will, together with you, look at some examples from Lavoisier. But first, some introduction. The last couple of years, what we have seen is that there is a renewed interest in inconsistencies from philosophers of science. Several people have already mentioned the work by Peter Vickers, but there is, for instance, also the volume that you edited in Synthese, was 2013-14, something like that, with a whole collection of papers on inconsistencies in the sciences. And the outcome seems to be that many of the authors that now many of the philosophers of science that are at this moment paying attention to inconsistencies in the sciences are somewhat downplaying the importance of inconsistencies. And there's also the idea, this is quite strong in Peter Vickers' work, but also John Norton has been promoting this view for a long time, that inconsistency handling is a matter of content, not of changing one's logic. And also this is quite prominent in Peter Vickers' work, is that scientists stop reasoning in the face of inconsistencies. And I have here the same quote as you had, so I can skip this one, it saves us already some time. This one is another quote from Peter Vickers' book, and it's related to a remark that Diederik made yesterday about Peter Vickers, that he seems to think that logical explosion only becomes a problem as soon as you derive a contradiction. So logical explosion via ECQ, contradictione, can only take hold if one first derives explicit contradictories. But then one will obviously notice this and stop making inferences. Scientists will, of course, recognize that any proposition inferred from a contradiction will not be and should not be taken seriously by the scientific community, even if the inferences used are all unquestionably truth-preserving. And then also about Bohr, there are numerous ways to reason with the propositions, and it may be that very few of these actually result in deriving contradictories. And when contradictories are reached, one doesn't continue and derive arbitrary proposition. One stops what one is doing and declares that something in the relation or assumption set needs to be changed, as Paul did. So these are some examples from some quotes from Peter Vickers. So what are the consequences for the friends of paraconsistency? Should we admit that the importance of inconsistencies has been overrated? Is the claim that non-classical approaches are needed, is that a mistaken claim? And should we now confine ourselves to the liar and other paradoxes? So the aim of today is to present some examples from Lavoisier and to formulate some thoughts and questions, and also I will try to say something about possible consequences or implications for scientific, inconsistent science and pluralism. Some background for the case study. So in this period, 1660 until somewhere 1674, there is a whole series of experiments on the role of air in respiration, combustion, fermentation, calcination. Calcination will come back later. So for instance, here what they did is, here there is a bladder of some animal, so something that is elastic, and you put a mouse here, and you leave it there, and what you will see is that, yeah, of course, it's a mouse that is alive, so it absorbs, well, there is respiration, and the bladder goes up. And what happens here, that's an experiment on combustion. So with a burning glass, you heat something, there's a candle here, so there's combustion, and here there's something, could be phosphor or whatever, that is burned. And here there is some liquid, and if this continues for a while, you will see that the water rises here. Now, so those kind of experiments by people like Bohr, Hooke, Meheus, and there were different theories. So it seems obvious if you look at these experiments that during these processes like respiration and combustion, something is taken from the air because the volume diminishes. And that was indeed, so there were many theories, but you could classify them in two categories. There were indeed theories where the main assumption was that something was taken from the air to explain that the volume diminished. But then there was another category where you had the opposite view, that something was given to the air. And you may wonder, how did they reconcile that with the volume decreasing and something is given to the air? Well, one of the ideas was that during respiration and combustion, some noxious things were given to the air, and because of that, the air lost its elasticity and it became more dense. So these were the two main categories, but within there you had several different views. And actually, each of these scientists had his own theory. So then a bit later we get the phlogiston theory, with Becher here and Stahl a bit later. And this is the cover of the book by Becher. And you see, if you look at the cover, this is really early chemistry. It's between alchemists and chemists. So the idea is that, I think most people are familiar with the main ideas of the phlogiston theory, that all combustible materials contain this substance phlogiston. During combustion, phlogiston is released, and this will become important later. Charcoal is especially rich in phlogiston. Calcination, reduction, we will come back to that later. We also understand in terms of phlogiston. And then this period, you have the chemical study of air. And so they were studying people like Lavoisier and Priestley, different kinds of air. So there was common air, I always put also the French term that was used. There was common air, that's simply the air that we breathe, the air that we live in, the air of the atmosphere, it was also called. In Dutch it was called gemene lucht. Then there was an air discovered by Black, fixed air it was called, and that's in modern terminology is carbon dioxide. So this is the air after respiration or combustion took place. Inflammable air, Cavendish, hydrogen. Nitrous air, laughing gas, Priestley, and there were several others. And so in those days, it was a kind of sport to do all kinds of chemical experiments and to try to get hold of the air that was released and then check whether this was an air that was already known or whether it was a new one. Calcination and reduction. So calcination occurs when you heat a metal in common air, then you get what they call the calx, and you get fixed air. So that is calcination. Reduction is the other direction. You start from the calx, you heat it by burning, for instance, charcoal, and you heat it, and then you get the metal back. Mercurius calcinatus per se, for instance, that's here, that is obtained from heating mercury. And Mercurius calcinatus per se will play a role later on, so that's why I already mentioned it here. And if you heat this further, you obtain again mercury.
Yeah, but mercuric oxide is an anachronism, of course.
Yeah, that's, yeah. Between brackets is what we,
Okay.
the modern terminology. 72, sometimes called Lavoisier's crucial year. To understand this, you have to see that Lavoisier, already before 72, had a very ambitious research program. So he wanted a kind of all-encompassing theory for all phenomena that somehow involved air. So combustion, calcination, reduction, respiration, fermentation, whatever process that in which air was involved, he wanted a theory that would be able to explain what was going on in those processes. And in 72, he turned to experiments concerning the combustion of phosphorus and sulfur, and he discovered, and he was not the first one to see this in the experiments, that if you heat phosphorus and sulfur, then the calcs that you obtain, you get an increase in weight. Now, this seemed like an anomaly for the phlogiston theory, because in phlogiston theory, the idea was during calcination, phlogiston is giving up. During the reduction later on, if you do that, phlogiston is again absorbed. But here what you see is that in the process where normally, according to the phlogiston theory, phlogiston is giving up, you have an increase in rate. And in 72, Lavoisier has the idea that something is taken from the air instead of something is given to the air. And there is this sealed note in November, sealed note that was, he wrote a note, he was often worried about not being recognized as the first who had the idea. So he wrote a note and then put it in an envelope and gave it to the academy, and then somebody sealed it and put some. So in the sealed note, there are things like this. About 8 days ago, I discovered that sulfur in burning, far from losing weight, on the contrary, gains it. It is the same with phosphorus. This increase of weight arises from a prodigious quantity of air that is fixed during combustion and combines with the vapors. And then he continues that he makes a very broad generalization that the same happens in all processes of combustion and calcination. And as some historians have remarked, at that moment he has very little evidence for that very broad generalization. But in this, if you look at the rest of the sealed note, the content of the sealed note, you see that in 72, in that note, he seems to be clearly giving up the phlogiston idea, and instead adopting the other idea that something is taken from the air instead of something is given to the air.
But does he explicitly say that? Or
yeah, well, if you understand,
I know that it's implied, but does he anywhere say explicitly, I'm giving up this? Or phlogiston theory is refuted?
Well, we have gain in weight.
yeah.
No, I understand that, but I mean, does he explicitly target?
No, not in that.
Okay.
You will not be saying that phlogiston theory is wrong, or
Mhm.
but everything he claims goes
Yeah.
against the phlogiston theory.
Yeah.
This period, 74 until 78, the discovery of oxygen, which is quite a remarkable story. So in 74, you first have Bayon, and he does some experiments on the reduction of this Mercurius calcinatus per se, the red stuff that I showed. And he found out, and I think there were others before him who did the same, but not in a very systematic way, that you can, and this is typical for this calx, as they call it, that you can do the reduction without charcoal. So for instance, with a burning lens or whatever, you heat it, and you get the mercury again, but without, so charcoal was seen as the thing that provided the phlogiston again. So you did it simply in air, without any provider for phlogiston, and you got the mercury back, without seemingly any phlogiston being added. Now, that was something strange. And Bayon also looked at, no, sorry, this should be the mercury. So you go from Mercurius calcinatus per se, you get mercury back, not the calx. This is the calx. You get mercury, and the air that then is formed, according to him, is fixed air. August of that same year, Priestley does the same. He does, like Bayan, he obtains oxygen, without knowing that it is oxygen, of course. And here it's right. So his first conclusion is that he obtains mercury, and that the air is nitrous air. He rather quickly rejects that conclusion and says that it's not nitrous air. He does some further tests, and it's simply common air. Now,
But that was different from fixed air, right?
yeah,
Common
yeah,
air?
yeah. Fixed air is carbon dioxide in modern terminology. In October, he tells Lavoisier what he has been doing. In March of the following year, Lavoisier does the experiments for himself. In that same month, Priestley effectively discovers oxygen. And by the effective discovery, I mean that he not only obtains this oxygen, but that he also realizes, he does some alternations with the experiments, he also realizes that he is dealing with something new. That is the first time here. So he realizes this is not common air, it's not fixed air, it is something new, and he calls it dephlogisticated air, air from which phlogiston has been taken. So in that same period, so of course one is in France and the other one is in England. So Priestley discovers actually oxygen, but Priestley does the same experiments as Priestley had been doing, and we will come back to that, to these experiments later. But he promised to present a lecture to the Academy, and that is in Easter 75. That's the famous Mémoire de Pâques, the Easter memoir. And there he has the conclusion that, also the same conclusion as Priestley originally had, that he obtains mercury together with common air, but there is a certain twist, and we will see about the twist later. But he literally writes that it is common air. In May of that year, Priestley corrects Lavoisier, saying, no, it's not common air, it is dephlogisticated air. And then in 78, Lavoisier publishes a revised version of this Easter memoir. And this is to complete the story about the chemical revolution. In a sense, you can only say in 89 or something like that, with the publication of the Traité, that is the end of the chemical revolution. But we will not see examples for this period. Now, this chemical revolution is a kind of paradigm example of scientific revolution. Everybody knows, I think, that it was used by Kuhn. But this is also an example of an interesting example of inconsistent science. Now, if you look at Kuhn's view, this whole period fits rather well in his scheme, and I actually have to thank Diederik for this drawing. I took over a course for the psychology students, and I used the slides, so now I use the drawing here also. So you have the pre-paradigmatic stage, that's where you have all these different theories, and then the first time that you have normal science is with the phlogiston theory, and then you have a revolution, and then you have again a period of normal science, and that's after the discovery of oxygen with Lavoisier. Now, this is from Kuhn. One of the interesting questions is, of course, what happened here? And you would expect that, given the title, but we all know that titles of books are sometimes misleading. Given the title of his book, you must find something in it on the structure of what is going on here. But as we all know, there's not that much on the structure of scientific revolutions in Kuhn's book. And this is what he is saying about one of the passages where he addresses the chemical revolution and Lavoisier's role in it. Lavoisier saw oxygen where Priestley had seen dephlogisticated air and where others had seen nothing at all. In learning to see oxygen, however, Lavoisier had also to change his view of many other familiar substances. He had, for example, to see a compound ore where Priestley and his contemporaries had seen an elementary earth, and there were other such changes besides. At the very least, as a result of discovering oxygen, Lavoisier saw nature differently. After discovering oxygen, Lavoisier worked in a different world. Okay? These are the familiar quotes from Kuhn. Now, the structure you don't find much more in Kuhn than this kind of story. You see it in a certain way, and all of a sudden you see it in another way. Now, what I found more interesting as a kind of image to understand what is going on in that long period, we will see 3 small examples, but it's really an extended period for Lavoisier, where he makes the transition indeed from the phlogiston theory to the oxygen theory, is that he's living in both worlds at the same time for a very long period. And here you see them going up and you see them going down, and it's the same for Lavoisier. You see it in both ways for a very long period. And the transition, he goes from one view, from seeing birds to seeing fish, but it's not by a sudden switch. For a long time he is here, both seeing birds and fishes. And so I think that's a more accurate picture to give, if you want to give a picture of what is going on there. So the examples now. The first one is, so I will not only look at published papers, but also at some of the notes, and that's why it's also an interesting example, because many of the notes are preserved. And there's also the book by Larry Holmes, Larry Holmes, who was a historian of science, and he made an excellent study of these notes. So I'm basing myself here on Holmes' work. This is a translation by Larry Holmes. It's a note on common air and fixed air. And in this note, he's asking the question, how do we get from fixed air again to common air? And he starts here from the idea, if it is true that the inflammable matter of combustion comes for the most part from the air, it would follow that air in which one has burned any kind of body is in part phlogisticated and in part deprived of its elasticity, and for the most part disposed to combine in solid or fluid form, and that is what in fact happens. So he's saying here, well, he's starting from the assumption during combustion, the inflammable matter of combustion is taken from the air. And now he asks, he says, but if through some means, whether it be, for example, by agitating in water, one succeeds in depriving it of all the fixable or phlogisticated part, then it returns to the state of natural air and becomes respirable and suitable once again for combustion. In order to convert fixed air into natural air, it is necessary, and it seems that he is going to give here a summary of what was preceded, but instead he strikes it out, and then he continues, one can thus convert an entire mass of common air into a mass of fixed air, so by combustion. He means he's again going here, connecting to the first part, by combustion. You go from common air to fixed air. It appears that in the same way, a mass of fixed air could be converted into natural air by providing it with inflammable matter. Now these are, to save time, I will not go into it. There are some other paragraphs below it, where he builds on the same idea that to go from common air from fixed air to common air again, you have to give something again to the air. Now, some people have claimed, like Holmes, for instance, that this first part is actually almost self-inconsistent because, as Holmes claims, in one and the same paragraph, he offers 2 contradictory explanations for the reconversion of fixed air to common air. The first one is that you have to remove the phlogisticated part. That's where he starts before he strikes out the sentence that ends with, it is necessary. What he writes below, the sentence the half sentence that he strikes out, is that you have to provide matter of fire to the air in order to become again, to obtain again common air. Now, my conjecture is that the first explanation, that you have to remove something from fixed air in order to obtain again common air, is immediately rejected. And well, one indication is that he stops the sentence And also the next paragraphs are consistent with that idea below the sentence, that the half sentence, namely that something is provided again to the air. Now what is happening here? He uses the old term phlogisticated air, and this is something I also looked many years ago to examples in early thermodynamics, examples by Clausius, where he made the transition from Carrillo's theory to his own theory. And you see also there that although he rejected the main ideas of Carnot's theory, he still uses the terms and the old terms. And often that's because the new terms still have to be invented. And you say the same here. In many of these notes, he's using the old terms. And these terms like phlogisticated air, they had different meanings. So it was, within the phlogiston theory, phlogisticated air was common air to which phlogiston is added. But it was also used to refer to air deprived of its elasticity, and to fixed air, and to burnt air. And within phlogiston theory, you can use all these phrases as synonyms. But of course, Lavoisier, if he starts from the assumption that during combustion, it's not the case that something like phlogiston is given up, but something is absorbed, then of course you cannot stick to the idea that what is left over is something from which something has been, something to which something has been added. And quickly about this, which mechanism, which logic. For me, this gives a kind of, so there is a problem here with the referring terms, and I have myself a very broad notion on logic, so I would also, if you have something with referring terms, in some cases I would also include that in the logic. But if you don't want to do that, you can also talk in terms of a mechanism. But it's for me, it's very similar to what you have in, for instance, default reasoning. I think even of the simple treaty example, okay? You make inferences from a certain referring term, and then some of these inferences are immediately blocked. And this, for me, this is one of conjecture of what is happening here. Second example, it's a manuscript, end of February 75, more or less in the same period as the previous note, and that's quite interesting that it is more or less in the same period, a bit later, but more or less in the same period as the previous note. So the first page is, so the note is about on the elasticity of elastic fluids. And the first page, on the first page is you get a quite systematic formulation of a theory on the three states of any substance. So it can be in a solid state, a fluid state, or a vaporous state. And he even starts with axioms, so very systematic. But then, as Holmes remarks, gradually the character of the text changes, reflecting on the way in which these principles could be applied to specific chemical substances and processes with which he had been particularly concerned. He seemed to be thinking out his explanation as he wrote, not knowing in advance quite where he was heading. So we have here, and I think I used the term later on, we really have exploratory reasoning here. He's almost thinking out loud. It gives that impression. So it appears very likely that fixed air is nothing but common air to which one has joined the same principle that gives nitrous air its permanence, and it appears established, in fact, that whenever common air is combined with the emanations from metals in calcination, it is converted into fixed air, and that it then combines with the metals and increases their weight, but it appears at the same time that the principle blah blah blah. I will skip a bit. First thing to note is that he assigns here in this paragraph two different functions to this matter of fire. Matter of fire was often used as a synonym for phlogiston. It has to maintain any elastic fluid in its vaporous state. The other function is that it changes one fluid from one state to another one. What is more important or more interesting even that there is a conflict with the notes from the previous example. In the previous example, he considered fixed air to be common air deprived of matter of fire. So common air from which something has been taken. That was central in the previous note. Here you get the opposite. Fixed air is common air to which matter of fire is added. So this is in line with the phlogiston idea. So fixed air is common air to which something has been added. And then, so he continues with a different kind of question. So now comes a series of questions. Why does agitation with water renders air respirable? And then he says, well, we have to make a distinction between two categories, acid airs and airs obtained by calcination, burning of candles, etc. And for the second category, these airs are basically nothing but respirable air altered by phlogiston. So to which something has been added. And he even uses the term, this is 75. In 72, he said that, well, in combustion and all these processes, something is taken from the air. 75, he is again using phlogiston and the idea that something is added. And so the question was here, if you pass this air through water, fixed air through water, why then becomes it again respirable? Well, if you pass it through water, the phlogiston is taken out and you get again pure air. Another question, why do combustible bodies burn only to a degree in air? Answer, well, combustible bodies cannot burn in fixed air. Why can they not burn in fixed air? I would answer that it is because the air must furnish its quota of the matter of fire to the flame. Now, the matter of fire being joined very intimately in fixed air, the latter does not let go of it. This matter of fire, on the contrary, adheres much less to ordinary air. But this answer no longer fits with the preceding ones, in which one has assumed that the phlogiston arises from combustible bodies. That becomes very puzzling. In French, he writes in French, of course, he uses even the term embarrassant, embarrassing. So he really derives here contradiction, okay? And it seems that he stopped there, but if you look at what he does the next days and the next weeks, he is again making all kinds of inferences from the same bunch of inconsistent statements and ideas. What is happening here? Well, the focus is initially on a different problem than in the previous example. In the previous example, it was quite focused. He wanted to say, he started from the idea that, like in the 72 note, that something is taken from the air during combustion, and then he addresses the question, how do we get from fixed air again to common air? Here, the problem he starts from is on the elasticity of bodies, and he starts from the old phlogiston idea. So he starts from a very different problem and a different point of view. But interestingly, inferences that were blocked in the previous example, for instance, that the part that where he changes his mind, they are not blocked here. They are even central to the whole reasoning. This is completely in line with what any adherent of the phlogiston theory would accept. Which mechanism, which logic? Well, my conjecture here is that if you look at it, you have here a kind of exploratory reasoning. The previous example is much more goal-directed. Second conjecture is that the logic is, well, his reasoning, if you want to understand it by logic, you need something that is quite rich. And all inferences that you see are classical. And does that mean that classical logic is used? Well, not necessarily. There is, of course, people familiar with the work of Vickers will know that Vickers often makes the transition from what I see in all these examples is that nothing but classical inferences. I see nothing but classical inferences, hence classical logic is used. But of course, well, everybody here will agree that that's a bit quick.
Very kind.
Last example, his experiments with oxygen. So in 75, he is doing the experiments with the reduction without charcoal. His expectation when he starts is that he will obtain fixed air. That was also Bayon's original conclusion, and that's also the expectation of Lavoisier when he starts working on it. He does the usual experiments, and all the experiments seem to indicate that fixed air is definitely ruled out. And this is in this period, so end of February, first days of March, his conclusion is that the air that he obtains is in the state of common air, so he's dealing with oxygen. So this is a conclusion about oxygen. The air is in the state of common air, except that it retains a little of the nature of inflammable air. End of March, he does the experiments again, and he starts with the test with animals. So you take a bird and you put it under a, how do you call this?
A bell jar.
Yeah, a bell jar, and you leave it there and you see what happens. But he did not wait until the bird was really dead. He removed it from the air, but it stayed there for a longer time than you would expect if it was simply common air. Then he turns to the nitrous air test. That was a test that was designed by Priestley and that was considered as much more reliable than these tests with birds and candles to test the quality of the air. And the nitrous air test is that if you have a kind of air that you want to determine whether it is something that you know already or whether it is a new kind of air, you put one part of it together with two parts of the air that you want to test with one part of nitrous air, so laughing gas, and you watch the diminution that you get. And I think the better, so the more suitable for respiration, etc. Combustion, the air is the more it is diminished. Now he leaves a gap here. So he says what he does at the beginning. This is a lab note. What he does at the beginning and what he observes at the beginning. So it appeared that the red color of the vapors was more marked and the effect more rapid than with common air. So the first observation seemed to indicate that he's dealing with something else than common air. There was a diminution of, so he will fill out later because he has to wait for a day or so. So that according to this operation, but he immediately writes down the conclusion that he will arrive at, so that according to this operation, it's not finished yet, one could judge that the air is more perfect than common air. Okay, he waits. What he sees that he obtains exactly the same diminution as he would get with common air. So instead of simply saying there is a diminution of so and so, he now puts all the details there. And then he strikes out, and then the new conclusion, that is to say, regarding the portion of nitrous air as probably entirely absorbed, there was 1 cubic inch, that is to say 1/5 of the air absorbed, that is about the proportion of common air. He does some further tests, so the lime water test, no precipitate formed, so this again ruled out fixed air, burning candle. You again get something, well, the nitrous air seems to indicate this is simply common air. The bird test seemed to indicate it's better than common air. The burning candle, one repeated the experiment of the candle 2 times and in large jars. It is charming. The flame is much larger and much clearer and much more beautiful than in common air, but in color, no different from an ordinary flame. Okay. So again, this seems to indicate it's something else than common air. Problem for Lavoisier, he promised to give a lecture to the Academy. Now, there is on the one hand, what several people already, Joe Smith and you in the same period, this early paper, Joe Smith is 88 and yours is 90, that if you have these cases of inconsistency, that you don't want to lose information. And we also heard it in your talk, that is indeed a concern. So he cannot simply leave out some of the results because he then loses information, but also if he presents a talk, he has to tell that he did all the experiments, otherwise they will say, well, how about this test, and did you do this test? These were the standard tests that you had to perform. So he has to mention all the tests, but some of the tests, well, all the qualitative tests like the burning candle and the bird, they seem to indicate that he's dealing with something that is better than common air, but the test that is considered at that time to be the most reliable one seems to indicate it's simply common air. How does he resolve that? So fixed error is ruled out, but is it common error or something else? This is from his Easter memoir. Now we can look at the, I know that here we will read the French, and we can look at the English. All these circumstances. So what he does is he presents all the experiments that he has done, and this is his conclusion. All these circumstances convinced me fully that this air was not only common air, but it is more respirable, more combustible, and consequently that it was more pure than even the air in which we live. Now, this is, I think, very clever. Okay? This is the only place in the whole Eastern memoir that he uses l'air dans lequel nous vivons, the air in which we live. In the rest of the memoir, he uses common air and air of the atmosphere. He uses that as synonyms, as was common in those days. But also, the air in which we live was actually in those days, for him, until he wrote this memoir, and for all his contemporaries, was also synonym. What else could the air in which we live be? What else can it be than the air of the atmosphere? But this is the only place where he uses it. So he's not putting here a blatant contradiction. He's not saying it is common air and it's not common air, but at the same time, there were synonyms for him and for the others. Okay. This is what he then, okay, well, what happens here, so Priestley does his experiment in that, so had done his experiments in March, and concluded that he was dealing with something else. And Priestley discovered this because he made variations on the nitrous air test. By changing the proportions, he got a diminution that was different from what you would get with common air. And that convinced Priestley, okay, now everything fits together. All the tests with birds and candles indicate that it's better. And also the nitrous air test, the new nitrous air test give me a different result. So it's something else. It is dephlogisticated air. Lavoisier corrects, says to, in print, writes that Lavoisier is mistaken. It's not common air, it is dephlogisticated air. And so later on, there is a revision. And this is the only change that he makes. So instead of saying that it is common air, he says, far from being fixed air, so fixed air is ruled out, it was in a state more respirable and more combustible, and so the rest he can leave as it was. What is happening here? Some historians like Conant, who has a small booklet on the overthrow, it is called, of the phlogiston theory, and he writes about this particular passage in the Eastern memoir. It is interesting to note how relatively few corrections and changes were required to make the original version of Lavoisier's paper correspond with the final and complete interpretation of his results. The similarity of the two versions, remember that it's only very few words in red that he changed. The similarity of the two versions is evidence that Lavoisier was very close to his final goal. Yet, the first version is almost self-contradictory. For the gas from the red oxide is common air, yet also purer than common air. For the moment, Lavoisier wanted to have it both ways. And that's indeed what is going on. He wants to have it both ways. He wants to keep all the information. At the same time, he does not want to put there a blatant contradiction, so he does a trick with his synonyms. Is it self-contradictory? Well, there's no blatant contradiction, but there's also no premature consistentizing, so by leaving out parts. But still, the problem is not solved. You can read it in a consistent way, and probably he himself and those that heard the lecture, they will have had some hypothesis, but there was no clear solution at that point. What is the logic here? Here we have a kind of different situation as compared to the previous examples. In the two previous examples, if we ask the question, what logic? Then we are asking the question, what logic do we need to understand the reasoning process? Here we have a finished text, so here we are more asking about what logic do we need if we want to not only see what are the explicit statements of Lavoisier, but also what the intended consequences are. You also need the logic there And there I would say that, well, my conjecture is that there is more than one candidate that you can use. You can, if you choose a consistent logic that is sufficiently rich, for instance, like CL minus, you could take that one, or you could take some inconsistency adaptive logic, or an ambiguity adaptive logic, or something Jaskowski-like. There must be several options. Asking which of these is the correct one, to me, that does not seem very fruitful. What I do think is important, though, is that whatever logic you choose, it should make clear that somehow the problem is not yet solved. And some people will prefer that this is clear by being able to derive a real contradiction from it. Others will say, well, no contradictions, but the fact that we cannot use aggregation, that's an indication that there is still something wrong at this place. So I think no matter how you realize it, the important thing for me is that somehow there should be a red flag, problem not solved here. And if you realize this by a contradiction or failure of aggregation, we cannot go into the head of Lavoisier anyway, so I think that's not that important. Moreover, I think the fact that if you try to go, or if you try to think of that kind of situations, it seems quite obvious that different listeners or readers, they also might have thought in terms of different logics. And maybe that's even beneficial in that situation where the problem is not yet solved, that people are using different logics to interpret what they hear. What can be learned from the example? So Lavoisier is struggling with mutually incompatible solution. There is ambiguity of terms. He does not refrain from reasoning. Even if for some particular note he seems to stop, well, the next day he starts a new note. He uncovers inconsistencies by reasoning. So this is in my questions to Bryson earlier on. Here it's not clear when he starts these notes, for instance, it's not clear where the inconsistencies are. He really has to make all these inferences in order to uncover them. He has a high tolerance for inconsistencies. He does not solve them prematurely. He does, at several occasions, we only saw one example, he tries to escape, especially in published or in papers that we read, to escape from blatant contradictions. But often these also contain, whatever he comes up with, often also contain some germs for solutions, so that it's clear that something has to be disambiguated here. Maybe we need two concepts, or you can start thinking about different ways to solve it. Is it rational? Well, somebody like Fred Müller that we had in the workshop that was organized by Dunya will say, well, no, this is too messy. He even used the term messy when he was in this workshop. Too messy, there is no logic, there is no rationality. So people like Fred Müller are only interested once you have finished theories and once it is clear and all problems are solved. Whereas for me, it's the messy part that I find interesting. So for me, it is rational, and even the passages where he changes his mind. If you well, unless you think that logic should be for God and for angels, we are stuck with our kind of cognitive apparatus, and we do make these things. We are limited in what we can keep in our mind at the same time. So this dynamics is unavoidable, and then to call it irrational because it is dynamical, it's strange for me. So you have this dynamics, but you have also self-correcting inferences. Which logic? Well, I don't think it's sensible to think that if you look at the three examples, they were quite different, that one logic is suited for all three of them. It's quite rich in every case, I think. There are many, I did not say much about that, but there are many ampliative steps, so not only deductive steps, but dynamic, monotonic, some more general questions, and I know I have to stop here, but I'm almost finished. Coming back to the beginning, where people like Vickers are saying, well, there are no real inconsistencies. So the question is then, are we looking in the same places? I see them wherever I look at interesting cases, I see them. So there is a difference, of course. If you only look at more or less finished theories, you will not find many examples of inconsistencies in the sciences. If you look at problem solving, and you find much more of them, so products versus processes. If we shift to looking at the processes instead of only looking at the finished products, you also see more inconsistencies. Yeah, Liaskovsky, I will skip now, you can come back to it later if somebody wants. Do we have the same view on logic? Well, I think I don't have to spend much time here on this. No required. Maybe I will end here, and then there is one more slide on pluralism. How to determine which logic is used. So this is I now learned from Bryson's talk, the Belknap question. So all rules used are classical, hence CL is used. We know that does not work, but you have something similar sometimes by difference of prior consistency. You find things like EFQ is not used, hence CL is not used. That's also not very convincing because, well, like Bryson also mentioned, you will not find examples where some scientists go from A to the same A preceded by 24 negations, but that is not sufficient to say, well, he's not using classical, nobody is using classical logic. And this is something similar. What you can sometimes do is that you can rule out certain logic. So for instance, if you see an example, an inference step where that is disjunctive syllogism, then you can rule out that LP is used. Lessons to be learned from CL minus. So whenever Vickers says, well, all I see are classical rules and it's very rich and it's very hard to, so CL minus is actually, so it's a logic designed by Dirichlet, everything you have in classical logic except for expansal, but all the rest you have. And it's very difficult to make the distinction between those two. What is the real problem with inconsistencies? For me, it's not that at some point scientists would start arriving that the moon is a banana or whatever. But the real problem is that they may start deriving things for which they do not have real support. And if you look at the examples of Lavoisier, also the fact that he calls it embarrassing, it's not because he derives a contradiction, but because he derives a contradiction, and for both halves, he has good support. Both halves of the contradiction, he has good support. And the inference steps all seem okay. So these are not trivial consequences. If you would then continue, for instance, where he says this is embarrassing after he derives a contradiction, if you would continue by deriving the moon is a banana and it's not a banana, you would say, well, that's not a problem. I don't care about that. But this contradiction, that's a problem. Okay. So he's not just deriving anything. He's deriving things that make sense. In conclusion, the transition from one theory or one conceptual framework to another one that is compatible with it requires simultaneously living in multiple worlds. This creates a period of inconsistent science. Is there one correct logic for this? Well, my view is that a pluralist stance is the most beneficial one. It's unavoidable, and it's beneficial to have this pluralist view. Thank you. Question mark because I didn't know whether we managed to do it.
Somebody else? I'm going to write myself in. Natalia?
Oh, I love the paper. Great, really great case study and full of interesting things. I think you're quite right in highlighting the importance of looking at those manuscripts and how science in the making is done, the puzzles, the complications. I love it exactly because it's messy. Right? And so it's crazy. So
also for other reasons.
Now, I want to ask you something about at the end. When you're saying, look, the fact, what before? This one. But when you're saying, look, the fact that it's false event is not used, then classical logic is not used, right? I agree that that's bad if you present that way. But there is another way of framing the problem that I think needs to be addressed. Right? The fact that an inconsistency is present, but no triviality seems to emerge, needs to be accounted for, right? And I think that calls for some story, right? Something has to be said, right? Particularly given the features of the case study that you offer, where it looks as though Lavoisier had reasons and good evidence for both things.
Yeah,
for what was going
there I
on.
completely agree. For instance, the contradiction that I presented there, well, in his note where he says this becomes embarrassing, this contradiction, neither of the two halves is a trivial consequence of the theory.
That's correct.
And that is indeed, there you can see that he's not using classical logic. That he considered this derivation as a sound derivation, whereas I think it's quite reasonable if you would, so I think in order to decide which logic was actually used, you need some kind of thought experiments or counterfactual thinking in the sense of, suppose that we would have confronted him with another derivation of another contradiction. So as soon as you have one contradiction in two steps, with things like this, you have another one. That most likely he would have rejected that one, but he did not reject the one that he derived. There he saw, this is a problem, that you derive in two steps that the moon is a banana and it's not a banana, that he would have said that's not a problem for me. But if he says that that is not a problem for him, then that means that he's not using classical logic. But because according to classical logic, his own derivation of this contradiction and the two-step derivation of the moon is a banana is not a banana, they are equally good. And we have similar examples, well, in the paper by Joel Smith. I'm referring to Bryson because I always connect those two papers that are more or less in the same period, and I think those were two important papers. In Joel Smith's paper, there is an example by, you will know it better than I, Planck's law, the two derivations, the derivation by Planck himself, and the derivation by Einstein. And Joel Smith's analysis is that Planck's derivation was rejected by Einstein and later by others, and there were inconsistencies involved. But the interesting thing is, if Joel Smith's analysis is correct, that the derivation that Einstein made also was based on inconsistent premises. But that one he did accept. So that you cannot understand from a classical point of view, because according to the classical point of view, both of them were correct. So that scientists are accepting some derivations in the presence of inconsistencies, and rejecting at the same time other that are, from a formal point of view, correct according to classical logic, that you cannot understand by classical logic. So intuitively, and well, I promised you that I would come back to my second question, the rational reconstruction thing and the anachronism thing. I think that if you make that kind of assumption, so if you want to understand the logic that they were implicitly using, of course, if you would have asked Lavoisier what kind of logic are you using, he would have said, well, I don't know, you're the logician, how should I know? But people like him who are who are making inferences in that kind of situation, and who are trying to come up with a new theory, I think it's fair to assume that they have good intuitions with respect to, okay, this is sensible, this is not sensible. And if you then come up with a logic that, for instance, allows you to see, well, okay, now I can explain if, for instance, something like this logic he was implicitly using, now I can explain why he accepted this and rejected that inference, then I don't see that there's a problem with something anachronistic.
Right, okay, yeah, that brings other issues.
Yeah.
And we can talk more about that. But another way of trying to account for the tension that Lavoisier recognized, right? Well, this is embarrassing, and I'm stuck with it. It's one way I particularly like, but it's one that is available in some sense. So when Harman wrote Change Your View, right, and he says, look, one thing is the logical consequence relation, and the other things, whatever you infer. And those things are quite separate. Right? The fact that, according to some logic, it follows, say, from a contradiction, everything, That doesn't mean that you're going to sit down and start inferring everything from contradictions. Nothing requires you to do that, right? So one possibility is to say, okay, although again, I'm not a fan of that strategy, but one could say, well, maybe Lavoisier said, look, if you were confronted with Filosóficas-UNAM in that context, he said, yeah, no, I agree, that's a consequence in classical logic, but I'm not inferring it. Right? I'm not required to do that inference.
Yeah, but I would want something stronger. That I think in that situation.
You don't want a reader of Lavoisier to, Lavoisier would not accept if the reader said, oh, now I know that the moon is made out of a banana.
Yeah,
Lavoisier would say, sorry, that doesn't.
Also, if you're in that kind of situation, and one problem is you want to localize the different problems, but you also want them to be real problems, so that you don't lose time with trying to resolve a contradiction that is a trivial consequence of your inconsistencies. And so that is why I said here, posting what is the real problem with inconsistencies. It's not that they would ever derive things that clearly are stupid, but that they might derive things that seem totally sensible and totally in line with whatever they accept, but for which they do not have support. And if they derive a contradiction in that way, for one of the halves they do not have support, then they should not be bothered about that contradiction. And that means that you need certain restrictions on classical logic. Otherwise, you have no words.
The question is how to tell when you have support or not, right? Because there's a sense in which, although Frege didn't realize that, but when faced with Basic Law 5, it does follow a contradiction out of it. You said, look, you never did that. Well, that doesn't take away the problem, right? You said, look, sorry, man, you have a system that is inconsistent.
But there you also have a contradiction that is not a trivial consequence. So by a trivial consequence, I mean, if you use this kind of combination like was on the blackboard earlier on, so variants of the, what is it?
I agree.
The Lewis derivation. Yeah.
Yeah, but again, you may have consequences that are not just simple derivations out of Filosóficas-UNAM, but you may have they would follow just as well. Right. So, for example, it would also follow from Basic Law 5 that I've also said and it's not a member of itself. Right?
Yeah, but that has nothing to do with expert support with that, right?
No, there is not. But I mean, there are a bunch of other inferences, non-trivial inferences, that would follow.
And you probably would be using those in the Lavoisier's case to sort of see, well, what could I do here? How can I separate this out and get somewhere with it? We'd be trying to do some substantive reasoning with these results.
And Frege was doing good substantive reasoning, right?
No, he was. No, I'm not taking that away. So I'm just puzzled about how can we tell? Well, of course, it's clear what will be trivial inferences, right? I agree that those people will just brush it off, right? However, there are a bunch of other inferences that are non-trivial.
But there I think this is why I don't know whether it will be an answer, but at some point I said there are different candidates and asking the question which one is now the correct one. In that type of situation, I don't know whether that makes much sense. And while preparing for this talk, I was also thinking about, it's a stupid analogy, but thinking about Duhem. In some of his texts, he makes a comparison between the French and the English style of reasoning, and it's clear for him that the French style of reasoning is superior to the English style. The French, they are able to reason in an abstract way. The English, they need models, and it has to be concrete. People say, well, this is a different style, and some people want something visual, and others want something abstract. And I think also here, well, I think in those situations, it's okay that some people say, well, the underlying logic here, I want it to be really really rich. Okay, if you have a really rich paraconsistent logic, like for instance C minus, then you will generate a lot of contradictions, and you have a lot of problems to solve. But it's very well possible that some people are best fitted. Well, this is the best situation for them to work in that kind of situation. It could be that others wanted to be more, and there I think it's a matter of what style of reasoning is best for that particular person.
Thank you.
So it's just a small thing. When we talk about, you use, Lavoisier uses the word en passant.
Yeah.
Because gênant, it's a false friend, right, of English. It doesn't mean embarrassing.
Is it not embarrassing? Okay.
No, it means that I've got obstacles in the way.
Uh-huh.
And gênant would be, I feel embarrassed. So I'm just wondering whether he used the word gênant or he used the word embarrassant. Okay,
It's
so
more like
so that
puzzling
means
than,
that there's an obstacle. So I
like
don't know if that
puzzling
changes.
of, and what was the English translation by Holmes? Puzzling, I think. Was it puzzling? So then it's more like puzzling or
Well,
puzzling.
it should be that there are obstacles. There's something,
Vexing?
there's something in it can be quite physical. It's like there's a chair in the staircase, so I can't go down the staircase.
Puzzling.
It's hindering.
Oh, yeah.
It's-
Yeah, that's better.
Yeah. Okay, thanks.
So
Thanks.
it's about my chair.
Yeah,
So
yeah.
it's just a small.
No, but that's good. Yeah.
But yeah, and I liked also the aspect that you're not saying that there has to be one particular logic. It's going to be a bit of a term of art or a bit of what is suitable for whom, at what point, for what sort of explanation, which logic you use. All that happens is you set parameter, you throw stuff out, right? You notice that disjunctive syllogism is used, therefore the reconstruction cannot include certain logics. That's all that you find out. And then you're still left with this panoply of logics you can choose from. That's okay.
Okay.
Just one final, first of all, I want to congratulate you for the nice talk. It was very interesting for me as a chemist. And also to the rest of the logicians, I'm not a logician, of course, it's that there is a role, I can see right now, there is a role for logic or logics, the different kinds of logics, and to try to make explicit or clarify our chemical thinking that we use normally and we are unaware of. So probably we can put it in a different level, and then we can realize what are we doing at the logical level, because normally 99.9% of chemists we're not thinking about this logical problems, which I think is very interesting. So I congratulate you for that. That's all.
Okay.
I think it's an open question, I guess, for the kind of program that lies behind the account you're trying to make of the case study, which I find fascinating. It's because I do some other, and I also study philosophy of science, but from another perspective. And it seems to me that there's an underlying premise that we should be able to account for processes of reasoning like that Lavoisier was immersed in, with logics understood from what I understand, and this is not something I know as deeply, logics understood as reasoning processes that are operations over symbols, right? So classical logic versus other kinds of logic. And I'm wondering what the perception is from all of you because when Octavio asks, how do you know when you have an inconsistency and it's I would say fruitful inconsistency, but that would be my account of the things. And when you have an inconsistency, it's just that where trivialities are being derived from it, and it's just, we would say using the idea that logic should norm reasoning, well, it would be irrational. And what my perception is that Lavoisier, in that inconsistency, what's more, maybe the the assumption that we should have a logic that accounts for that, or we should make one of them up, is a bit ambitious, and maybe cognitive science would have something to say. I mean, something more descriptive about how we react and work, and how scientists actually get engaged with the material. Because maybe one answer to Otavio's question is, well, maybe Lavoisier, I mean, Lavoisier was clearly the experiments you mentioned, he had to develop a series of skills, and he knew gases in a very like physical way. Like he knows how to tell the color of a flame. He could tell that there was something else going on just by, well, not just by the color of the flame, the bird living longer. And maybe there's something about just like that more experiential interaction with the materials that can account for these reasoning processes that cannot be accounted by a logic that operates at the level of just processing over, I mean, propositional relations between propositions. And
That would be the ampliative.
Yeah.
Right?
Yeah, it's kind of inference to the best explanation or something. Yeah, that I did not go into it, but well, often there is a kind of when people. Sorry, I'm getting a bit tired. Kind of overemphasis on the deductive steps, but in these cases where you have these transition period, you have a lot of ampliative steps. By these I mean non-deductive steps, where the conclusion contains more information than the premises you start from, and even in some cases, the contradictions that you generate are generated by ampliative steps, or in part by ampliative steps, and not only by deductive steps. So, for instance, you come up with two explanations. So an explanation for one set of experiments and an explanation for another experiment, and they turn out to be incompatible or mutually inconsistent.
okay.
I'm struck by this sort of, as you say, refusal to carry on in what might be said to be a logical way once you've got this contradiction, and carry on inferring ridiculous things. And wondering about how we can describe what it is that he's stopping doing, and whether what we want to be thinking about, the question I want to pose is, but what we want to be thinking about here is not logical limitation, or whether it's got more to do with the way in which we reason with predicates in the scientific region, or words for natural kinds and so on. So in the chemistry that he's working with, he's got some ideas of various natural kinds, and he's got some material rules of inference that govern reasoning with that vocabulary.
Yeah.
And so rather than go to infer something that the logic would give you, the classical logic would give you, he's focused on, and I think most scientists are when they're doing reasoning, on the rules that govern material reasoning about the predicates and the natural kind terms that actually are present in their science.
Yeah.
And he's struggling within those rules to find a way out, which is really ultimately forcing him to change those rules in some way.
Yeah. I think if I understand you well, I think we agree there, because, for instance, the first example, there for me the problem is indeed with what I would call the referring terms, the non-logical terms.
Mm-hmm.
But the situation here is a bit more complex. He's indeed making all kinds of inferences based on the meaning of non-logical terms. But at the same time, what are the natural kinds here? Is phlogiston still a natural kind? In some contexts, he's reasoning, okay, now I give up the idea of phlogiston, but then he still uses the term phlogisticated and dephlogisticated there, and then, he finds himself making inferences that he says, well, I don't want these because...
So you're actually transforming the meanings of these words as you work with them, because you keep running into trouble as you try to apply them and apply the rules that go with them.
Yeah.
But those rules are material rules, they're not general rules for predicates. The reason the predicates, they're material rules about how certain kinds of results should follow if indeed this term is correctly applied to the substance you produced.
Yeah. I'm not sure I'm following completely now, but for me, I made a comparison at some point with default rules, like take the treaty example. Yeah, for me, those kinds of inferences, I would also say, well, that falls under logic. You can make inferences. So if you have one of these old terms, like phlogisticated air, you can make inferences. But if it contradicts something which you infer from the opposite view that you are developing, then you have to withdraw them. If they are not consistent, so when he derives, well, if I want to go now from fixed air to common air, I have to take something out of the fixed air. Well, that is in contradiction with what he's now trying to develop, namely that fixed air is something from which already something has been taken. So if by taking out more, you will not return to common air again.
So you're restructuring those rules, but those rules have to do with these substantive terms in science, not logical rules that the classical logician or some other logician bring to the table.
Yeah, but that is also one of the reasons why I would say, most likely you will not have one logic or one mechanism that can deal with all the examples. So the first example for me that is most likely related to the substantive term or the terms or the non-logical terms. But for instance, the second one, this exploratory reasoning, well, there I would say, well, this is take a very rich pair-consistent logic, and then you can understand the steps that he's making. He's simply he goes from one question to another question, and by going to another question, he brings in also other ideas, and he just is making inferences to see what follows and what he can combine, and when he arrives at contradictions and when not. That seems to be a different situation than the first example. You do not agree?
No, I think well, this very rich pair-consistent logic will not help you. I couldn't even understand that you would use CL minus, but I think there should be, because CL minus produces a lot of inconsistencies, and then you have to get rid of all of them. If you use it in some other way in adaptive logic, whether inconsistency adaptive or otherwise, you minimize the inconsistencies. Yes. But with your very rich pair-consistent logic.
Yeah, but I agree, but even within the inconsistency adaptive approach, you still have options how much you restrict it. And there I would say, well, there may be individual differences there. Some person may prefer something that is really restricted, and another one, well, I usually prefer something that is a bit wilder. You would like to restrict it to one contradiction, and so could be that for logic.
It's just a quick, well, it might be something to think about. The notion of taking away, so you can take away one thing, but that taking away might provide space for something else to enter, right? So the taking away doesn't necessarily have to be negative, or it can have a positive effect. So another way that Lavoisier might have re-reasoned was that one of the taking away was actually giving of something else. I mean, because there's a symmetry between giving and taking, right? And there's a negative taking away. So one could have rethought.
Yeah, well, there must certainly be notes where he's exploring that kind of.
Right, that's part of that tension too. Right?
But also already, and that's the interesting thing. Also, one of the interesting things also of this case study, already before the phlogiston theory, you have this tension between giving and taking.
Right.
And already then you have the combinations of the two.
Because there are different conceptions. One was about weight, another one was about volume, another one was about energy, right? Or giving combustibility or something, So
elasticity.
So these are different notions that might, could have, at some point in the reasoning, one might have been the complement of the other or something.
Yeah.
Yeah. And conceptual.
Well, something that is a bit related to that is that you have here, of course, the enormous advantage of doing this in natural language. You have this flexibility, and you can come up with all kinds of possible hypotheses and different ways of looking at it. If you would immediately formalize it and do it with P and Q, and you would not have this same flexibility, and you would
That's
not arrive at the oxygen theory.
And then as Alfonso and I were saying, that vagueness and that
Yeah,
flexibility is what gives the richness to
Yeah.
the science and allows the science to go forward.
Yeah.
You don't fix things prematurely.
Now, how much of that, of the process of going back and forth, of taking it back, actually gets into the final version, right? But I know you didn't have time to cover the book eventually when he sort of systematized what happens there. So is the story then one in which, okay, here's oxygen, here's how the experiments that support that's what's going on. And then all of this struggling process
this would be
is
so.
basically
Yeah.
ignored, right?
Yeah, yeah. Well, you can think there also of, I don't know whether you know these terms that were introduced by Tom Nichols. It's an ugly word, but discoverability. And you have that also with Lavoisier. Once the idea behind discoverability is that once the problem is solved, scientists tend to make a coherent story about it, how it could have been how it could have been discovered, and they make something systematic, and that you have also here. Once everything is solved, then he makes a coherent story and a systematic story, and that you have.
Kekulé is an impressive example of that. Completely fake.
Who?
Kekulé,
Yeah.
the story by Kekulé is completely fake.
Yeah. No, because one concern there,
Just makes
right, is, okay, so then, once you look at even the final product,
Not his own
Yeah.
right,
invention.
and you don't find any of these tensions anymore,
No.
right? Then you can say, look, you do have an inconsistency, or at least in the pursuit of what the proper account was, but eventually that's
Yeah, of course,
eliminated,
of
right?
course.
So,
That's also why I said if you take Kuhn's view that it was simply shifting, and there's no need for anything else than classical logic, because phlogiston theory is consistent, and oxygen theory, what Lavoisier ends up with, is also consistent. So if it were simply a matter of switching, and if you could never have somebody who was living in the two worlds at the same time, then there is no need at all for anything else than classical logic.
right, so, okay, I want to press a little bit on this about the words, what worlds talk.
Yeah.
Right? Because, of course, Kuhn got a lot of trouble out of presenting things in that way.
Yeah.
And in a way, understandably so, right? Because it's very mystifying, right? He set up paradigms as these fundamentally incommensurable structures. And then, of course, you look at one paradigm, look at another paradigm. How come, if they're incommensurable, how you can have people thinking through both of them? Of course, he encouraged that exactly because of presenting things in such striking terms. Now, he himself knows better, right? That you, of course, you're able to understand the conceptual machinery of one theory, the conceptual machinery of the other. You see that there might be tensions between them. There are different ways of conceptualizing the phenomena. But I think it becomes very misleading, right? To present this as, oh, look, you have these two different worlds. You have two different descriptions of a certain phenomena. There might be tensions between them. But of course, even to say that, you have to overcome incommensurability. Right? You have to be able to say, yeah, look, when you're talking here about the desiccated air, now maybe you're actually already thinking about something quite different. That it's better thought of in terms of a new element in a different system.
If I may just jump in, for instance, hazard chance analysis in this case would argue totally against your removal of this world. So, or it doesn't matter about the world, but the idea of this being very distinct ways of doing chemicals practice. So it's not just that we have different description of the world, it's the way, the basic principles which guide the science in this practice are quite different. So he's using the term compositionality, I think, for for Lavoisier's approach, and there is some other term I don't remember from his book on water for the logistic chemistry. And so the way how they are approaching objects which they inquire are completely different. So that's where the tension comes from. It's not just if you say, let's look at this way, let's look at this way, which Chang also says it doesn't mean that the scientist cannot switch between, he's using exactly a dark rabbit picture, or to say that scientists can, just like we can switch to that, so can scientists. But that doesn't mean that this practice can be reconciled in one.
Oh yeah, no, I agree, and I'm not denying that, right? It's just that it's not the world that has changed, right? What changes your description, plus a bunch of other things, right?
Who would say there is no world in itself? There is no world independent of our theoretical. But who disagrees with that? I mean, he would say he's very Kantian in this. So he would say the world in itself is something we don't know what it is. So who cares about this world?
Yeah, no. Look, that's exactly what I find. I love Kuhn, right? I think a lot of very insightful things, but also extremely misleading things. And I don't see what he's gained out of. Well, he got a lot of people talking about the work, right? And pointing difficulties and so on.
Some of that stuff licensed things
That's right.
troubled us since.
Yeah. So, and he of course had to recant later on, right? So no, look, it's not that radical. It's not like so dramatic, and so that's why
I think in a sense I may agree. On the other hand, for me the world talk is just a kind of metaphor to say, well, we have completely different conceptual frameworks.
that's perfectly fine. And
For me,
if
that's
how it's meant, I have no problem. Right?
that's all what I understand by it.
And I think eventually that's what Kuhn means.
Yeah.
Despite he may deny that it's not as sexy or whatever, but
I don't agree. Who
But
wouldn't go that far? No way.
he
Because
gave
this
up
man
the
is
theory,
philosopher.
right? When he introduced disciplinary matrices, he's giving up that.
Yeah, but he gives up correspondence theory of truth. So that's why he can't go as far as you want him to go.
Oh,
He
no,
gives up-
I never say that he's a realist, right? But I don't think he goes as far as say, look, I don't know whether there is a world out there. He's Christian, for Christ's sake, right? There are documents, there are pieces of things.
No, that's clear.
So,
It's just how you carve up the world. It's not predetermined.
yeah, but the world is one thing, the world is another thing. So you can carve up in different ways, but the thing is going to be there, doing its thing, or not doing its thing.
Yeah, it's a different meaning.
But not sufficient.
Yes.
All right, okay. Enough. Today is just, Tuesday, right? It's not my skeptical day. Tomorrow.
Luckily tomorrow we have a workshop.
There you go.
Does anybody else have a question or remark? Okay, so we should thank And I think you're all invited to dinner in
Since I am the youngest, I think all the speakers thanked you and Maria, but I think we should also start a big hand
Yes.
for the organizers.